valuable support in establishing the collaboration between our faculty and the external community. And I would also like to give the senior thanks to Mr. Chairman from the for his professional mentorship and the technical guidance throughout this project. And moreover, this project I have done work with my partner, LVTN, and in my presentation, I will focusing on helping you to understand the entire project workflow, while the detailed result will be presented by LVTN in this following section. This is my outline of the presentation. We will start with the introduction, the research model and simulation tool. As you can see in the figure 1, our research model will focus on the OC4 distribution system. The methodology, the result, the conclusion, and the future work. And for the introduction, as we are aware of, the world is making a commitment to reach the net zero goal by 2050. And this presents both challenge and opportunity, especially for Vietnam. With 3,000 kilometers long coastline with strong and favorable wind through the year, Vietnam is well suited for developing the wind energy. But most of Vietnam offshore region are in the deep water area where the traditional foundation turbine is not viable. The floating offshore wind turbine comes into play, but it offers the challenge. First, the cost control of manufacturing the semi-submersible platform is very high. And secondly, is the complexity of the spread management and the complex dynamic analysis from the aerodynamic and aerodynamic response. Therefore, our project is aiming to develop a hybrid machine learning and finite element analysis workflow to reduce the cost and deliver the reliability and efficiency design. As you can see in the figure 3, this is our general workflow of our project. We will have two main phases, the analysis phases. We will start with the structural analysis of multiple variants of the OC4 configuration for creating the data set. Currently, we are having around 1,900 different cases for training the machine learning model. If the machine learning model shows good results, we will come to the second phases, in the design phases, where we will require the model to deploy in forward and inverse way. For the research model, as I said before, we will focusing on the OC4 distribution system, which is a 5 megawatt wind turbine developed by the NREL. And to streamline our project, we will only focus on the semi-submersible platform, and the tower and turbine will be transferred into equivalent forces. And the reason for us to do this approach and also this model, because the OC4 distribution is a baseline model for a 5 megawatt floating wind turbine, and this is well documented and validated in the research community. And the semi-submersible prop is considered as the most expensive prop of the entire system. It's accounting for 35 to 40% of the total cost. And as you can see in figure 4, the semi-submersible platform considering a main column in the middle with diameter 6.5 meters and surrounded by 3 offset columns, including the upper column and the base column, connecting by 15 pontoons. And it has a mooring system including 3 catenary lines with the arrangement illustrated in the figure 5. For the simulation tool, in the figure 6 is our detailed framework. We will start modeling the variation in spike length. After that, we will use OpenFast to obtaining the moving forces and the tower load. And we will fed into ANSYS as one of the variable conditions to do the spread, to do the structural analysis, to obtain the data set for the machine learning model. And for the machine learning model, we will use a normative framework called AISA. This is developed by the ATH Zurich in Switzerland. And for the methodology, in my presentation, I will focus on the red block, which is OpenFast, including the OpenFast setup and automation script from the databases, and the variable condition setup and machine configuration in the ANSYS. For the OpenFast, the simulation case we focus is the static equilibrium with no air and still water condition. It is the descriptionary log K1.2 in task 30 of developed by the IAOB. And you may wonder why we do such simplified condition, because the main reason is due to the time constraint of our project. We only have around 3 months to do the entire project from scratch, and the main objective currently is to create a workflow that can be developed in the near future. As you can see in the figure 7, we compare our moving forces with the order of participant in the IAOB task 30, and our results show good agreement with the published result. To handle multiple cases of the configuration, we have developed a Python script to execute the OpenFast automatically. The script, as you can see in the figure 8, the script will define the modified dimension, including the main column radius, and it will modify the parameter necessary to run the fast. For example, new mass inertia, the plus adjustment if the material change and geometry changes, the connecting members, coordinate in hierarchy, and the failing coordinate in modal, and it will run moment fast. And this script enables us to handle all the parameters programmatically and minimize the human error. And as you can see in figure 9, this is the change of the moving forces across the geometric variation. And you can see that the beam length and the column diameter have a significant influence, while the height, column height, and the thickness have effect but minor. And the moving forces are symmetrical across different columns. And from the figure 10 to figure 12, we can see that the trend of moving forces is consistent across different materials. Similar with the figure 13 to figure 14. And come to the mass, due to the limitation of the total number of elements in the ANSYS student lesson software, we choose to combine both cell element and beam element in order to maximize the total number of cells in columns and the contour connection. You can see in the figure 15, the cell element will be distributed on the column and stiffener, while the beam element will distribute on the contour. For the boundary condition setup, we choose to use the elastic supporting inertia relief to mimic the behavior of the platform while preventing the rigid body motion. Coming to the result, in my result, I will focusing on the result of the analysis phases, including the global analysis of the baseline OC4 configuration, internal spread and deformation, and the sensitivity analysis. As you can see in figure 18, the baseline model can withstand with the current loading condition. The high spread concentration is at the central brace contour, the base column, and the contour connection. And you can see that the highest spread occur at the YLNC connection. And this is the main reason for us to choose this connection behavior as our output for the machine learning model training. And in installed deformation in the figure 19, we can see the symmetrical pattern of deformation at the bottom column center. And the reason for this is about the absence of the ballast water in that region. For the sensitivity analysis, the purpose of it is to understanding the effect of the parameter in the model behavior. And you can see that the radius and column height have the negative sensitivity in terms of connection, spread, and deformation. This means that if we increase the column radius or height, the spread and deformation at that connection will decrease. In contrast, the beam length have a positive sensitivity. For the structural masses, all of three external parameters have nearly linear relation with the structural masses. And for the internal parameter, we can see that at aluminum alloy, the highest spread and deformation occur, while lowest at the carbon fiber. And after the cross section occur the highest spread and deformation at the square cross section. And you can see that the column thickness had nearly zero effect on the change of connection, spread, and deformation. And for my conclusion, I have presented to you the workflow for combining OpenFast and MANSIP for analyze and creating the set for machine learning model. And in our project, we have developed a hybrid machine finite element analysis and machine learning model, and it will present later by you. And for future work, we will expand the training data variety, optimize the hyperparameter calculation, and start with element analysis, and that's all.